Okay, parallel circuit that we have here, again, we have 12 volts for our pressure in the circuit. We have 1400 ohms at our diode here, 2200 ohms at this diode, and 3200 ohms at the third branch here, the resistor. So again, in a parallel circuit, what's unique about parallel circuits compared to series circuits? I'm sorry? Yeah, more than one path. What stays the same? Yeah, the pressure stays the same, because if I take a reading on this side or this side of this component, it's the same because the pressure is coming out here to both sides, right? So the voltage stays the same in a parallel circuit, and that makes it a little bit nicer for us, less to solve for. So 12 volts. Total current here, again, our formula for current is voltage divided by resistance. We know our voltage, but again, we do not know our resistance yet, so we need to figure out a resistance. The formula for that resistance, some of you probably had to look back, but it was that 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3, so on and so forth, depending how many of those components you have in there, okay? So you should have put in there 1 over RT was equal to 1 over 1400 plus 1 over 2200 plus 1 over 3200. When you add it all, when you got that, if you just did this section right here, you should have got an answer of 0.00148 and change. Okay? Now, what didn't I do yet? I didn't do the last reciprocal, right? So when I take this and I do that last reciprocal right here, 1 over, you actually get a total resistance answer of 675 roughly. Now, depending on how many decimals you carry, or how many places you carry, I should say, you may have got an answer somewhere in that neighborhood. So I think Ryan over here at 680 I saw, which is acceptable for this. Okay. So I can take that number, plug it back in up top here. So for me, I had 675. Take my 12 volts divided by 675, and I get a total current of 0.0178 amps, or 17.8 milliamps. Okay. Again, is that a lot of current? 17.8 milliamps. If you touch a circuit and it had 17.8 milliamps, would you even feel it? No. Nah, you wouldn't, because the stuff that we've been doing already is somewhere in that 20 milliamps, a little bit over 20 milliamps. You don't really feel it, right? When it starts to head a little bit higher than that, then you'll start to feel it just gently. Okay. All right, so with the parallel circuit, Kirchhoff's law is the current law, which says that the sum of the branches, the sum of these legs, equals the total current. Okay. Well, we found out the total current was this 17.8 milliamps, so let's prove. Let's make sure we got this right. Since voltage is the same in all, and to solve for current, it's volts divided by resistance, I'm going to keep the voltage the same in all. The thing that changes is my resistance. So for the first one, and I know I'm squishing here, I apologize, was 1400. For the second one, it was 2200. And for the third one, it was 3200. Okay, if you did the math here, you should have gotten an answer. And again, I'm going to round a little bit to make things easier. So somewhere in that neck of the woods, depending on the number of places you carried there. Okay, when I add these three together, guess what it equals? What you had, well, not the voltage, right? This is the current one, right? So up top here we had 0.00178. I rounded. I actually got, it was like 0.01777 amps. So it ended up being pretty close to proving that law. Okay.